Okay. So, yeah, this is application of the differentiation. Tonight we'll look at one form of application. That is where we're just trying to take advantage of the maximum and minimum. So if you go through these questions, they all have one thing in common. They are all talking about either something being minimum at some point, largest area, that's a maximum. And then here again, largest possible area. And then even here we have the square of the other. And then basically the last part here, maximum. So that's one thing these questions all have in common. They all talk about something being maximum at some point. Then I think in tomorrow's class, we're going to look at how we now take advantage of a differentiation in terms of a rate of change that it is. So how do you approach this? Well, at a maximum or a minimum, what we know is that a derivative will always be equals to 0 at a maximum. So if the function that is changing is y, or the variable that is changing is y, and it's changing with respect to x, then we understand to say that if the y is to be maximum, then its derivative at that particular point will end up being a 0. So this is literally what we are trying to take advantage of. But how do we actually take advantage of this in different situations? The questions are changing from easy to hard, perhaps. And like I said in the group, I would leave 11 for you guys to try out. But if you guys struggle, just let me know in the group and I'll forward the solution. I'll work it out and forward to you guys. So start from here and do work it out until when you reach somewhere here, with 10 being the most complex for us tonight. So let's look at the first one here. In the first one, they're saying that we have two negative numbers whose sum is 60. So we have two negative numbers whose sum is 60. And what we're looking for is what are the numbers if the product of one of them and the square of the other is maximum? So the first thing that the question tells us is that the numbers are negative, so two negative numbers. When you add them, you get a 60. So the sum of these two numbers is a 60. So let's say the two numbers are A and B. So you can say X and Y, or you can say A and B, literally anything here. So when these two numbers are added, so I'll say A plus B, we get a 60. So of course, we know to say these two numbers are supposed to be negative. So perhaps if we say negative A plus negative B, then the answer would say minus 60. That is if I would decide to go with the negatives. But since I'm seeing my answer here, my sum is taken as a positive sum. So I'm assuming we know to say these numbers A and B are negative, yes, but the sum we're just taking more like just the magnitude of their sum instead of the fact being that it will be negative as well. So just dealing with their magnitudes there. But it's okay. You can still approach it in terms of the negative part. But in this case, let's approach it in terms of just trying to find what the magnitude of A and what the magnitude of B is. So when we add these two numbers, we get a 60. Now, what will be A and what will be B? Well, to find what A and B, what they are, we now have to look at the second condition. The question says, what are the numbers if the product of one of them, so the product of one of them, let's say the product of A, so the product of A with what? Let's see. The product of A, one of them, the product of one of them, and the square of the other. So here, it's not the product of the two numbers. It's the product of one of them and the square of the other. So I'll get the product of A and the square of the other. The other is B, so I'll say the product of A and B squared. So what are they saying about this product? That product has to be maximum. So they're not saying anything really about what it's supposed to give us. All they're saying is it's supposed to give us the highest possible number. So this product is supposed to give us the highest possible number. Let me call this product to be a variable y. So in other words, we're saying that y is equals to a b squared. This is what is supposed to be maximum. Now, for this to be maximum, what has to be the case? Now, that is where the condition we labeled earlier on, I erased it, comes into play. If this is maximum, then the derivative of this product with respect to a variable there. Now, the question is, with respect to which variable? We'll see that in a minute. So with respect to a variable, this has to be equals to 0. Currently, this is a function of two variables, a and b. So the easiest way we can approach this is go back to equation 1, where we had a connection between a and b, so that we can eliminate one of the variables there. And since we had a plus b being equals to 60, this would imply that I can eliminate any one of them. Let me eliminate b. We can say that b is equals to 60 minus a. So that when I substitute this into equation 2 was y is equals to a b squared. This now becomes a, and then we have 60 minus a. And then this has to be squared. From here, we can work it out the way it is, or you can expand what is inside here. So let's see what we get. So we have 60 multiplying 60. That is 6 by 6, which is 36. Then with just 2 zeros. Then we have minus 60 and a, that is 60a. We know it to come again, that is minus 60a again. And then plus a squared. All this is just expanding what is inside, what is being squared there. We'll send in the a. This becomes 3600 with the a outside. And then minus, when I add these two, I'll get 120. But I have this a, the one that they carried initially, then multiplying that a with the one coming from outside, we get a squared. And then here, this was just a squared, then multiply it with this a as well, we get a cubed. So we have plus a cubed. So I hope you guys are going through this just in case I make some silly mistake somewhere. So this is what our function y is now equal to. We can rearrange so that we start with a cubed, then we have minus 120, a squared, then we have plus 3600 a. Now, since this is the function for their product, we can then try to determine when this is going to be maximum. For this to be maximum, then the derivative of this function with respect to the changing variable, in this case, this is in terms of a, this has to be equals to 0. So let's differentiate y with respect to a. Let's see what we get there. Of course, this differentiation is distributive, so you can just differentiate one term at a time there. So we differentiate a cubed, we get 3a squared. The second term, when we differentiate, we get minus, this is 120, so get 240 a. And then the derivative of the last one, that just becomes plus 3600. So this is the derivative. Now the question says this is supposed to be maximum. So of course, taking into account what the condition for maximum is, we can then just equate this function to 0. So that what we now have is 3a squared minus 240a plus 3600. This has to be equals to 0. So we've now reduced this function to just a quadratic equation, which we can solve every other day. So I'm trying to see if this can, I think it can reduce. 3 can go into all these functions or all these terms. When I divide through by 3, I get a squared minus 80 here plus 3 here goes once, 3 there goes twice. This is now what is equals to 0. Okay, now we want to see, is there an easier way of working out this, or we have to go through the longer method? So if it's possible to work it out using factorization, you can go ahead. If not, then we'd have to use the quadratic formula. So what do you guys think? Is it possible to work it out using using the shortcut. So here I'm substituting into the quadratic formula. My b is negative 80. My b is negative 80, so I have minus 80 here. Then plus or minus the square root of b squared minus 80 again. Then minus 4. A, then we have our c here. Okay, usually when you have A and C being positive numbers, you always want to be worried a little bit, because if A and B are positive numbers, are both positive, then you're scared, what if this term here ends up being greater than this term here? Then it would mean that maybe you made an error somewhere, because you want this difference to give you something which is positive in the end. So let's see if we'll run into that problem. So we have 80 here, plus or minus the square root of. So you have 80 squared. That's 6,400 minus. Then we have 1200 multiplied by 4. Well, lucky for us, we won't get a negative number. Then this is over 2. If we simplify this, the difference there, at 6,400, less our previous answer, we get 1,600. So we have 80 plus or minus, then the square root of 1,600, we get 40. Well, it looks like it was possible to actually solve this by factorization, I guess. And then this is over 2. So that we can now say that our A is equals to 80 plus 40 over 2, or 80 minus 40 over 2. So that here we get, when it's plus, this is going to be 120 divided by 2, which is 60, or when it's minus, this is going to be 40 over 2, which is going to give us 20. So these are the two possible values of A. So from here, having determined what A is, we can then go ahead and determine what B is. Remember our expression for B? We had this one. So since this is what gives us B, we can now just substitute. If A is equals to 60, then B will be equals to 0. That is if A is equals to 60. Of course, we're going to have 60 minus 60, which gives us a 0 for B. But if A is equals to the other term, 20, then we get B is equals to 60 minus 20, which gives us B is equals to 40. So our two negative numbers, in this case, we can say we have two sets. We can say either A is equals to negative, that's negative 20, and B is equals to negative 40. Or we can say A is equals to negative 60 and B is equals to 0. So these are the two possible sets that we can have that satisfy that condition.
Now why are they negative again? We get positive numbers.
Okay, so when we are calculating them, remember I said we're only dealing with their magnitudes. The question said what? Two negative numbers.
So
Yes, please.
since 0 is not a negative number, do we have to get rid of it and just follow the negative 20 and negative 40?
Yeah, if you argue that 0 is not a negative number, then you'd eliminate this pair. Not this pair, sorry, this pair. And then you'd only go with these. Okay, any questions there? Anything else? Okay, so I hope we've got that. Kangwa, you got the answer to your question as well?
Yes, I have.
Okay. So this answers that question. I want you guys to notice that it's the same trick with these questions. It's the different conditions that they give you, but the idea is always the same. Come up with the expression based on the constraint that they've given you. In this case, the constraint they gave us was the fact that the product, it was that the sum has to be 60. That was the constraint, the limitation. The sum had to be 60. Now, the other thing that they gave us was a working principle, which is the product of one of the terms with the square of the other has to be maximum. That was the working condition that we had. So because of that, we were able to pull it out. So let's look at the next one. For the next one again, find the largest possible area for an isosceles triangle if the length of each of its two equal sides is a 10. So again, they're giving us a limitation. And the limitation is that the length of each of its two sides is a 10. So this has to play a role. And then the thing that we want to determine is, or what we're working on. Yes, please.
I have a question.
Go ahead.
So just something that's been confusing me.
Sure.
Finding the maximum, the maximal.
Mm-hmm.
Is maxima and maximal and maximum the same thing first?
Yes.
Okay. Secondly, when we're finding at stationary points and just like this, it's different. Is it different?
No, it's not different. In fact,
now,
yeah.
What about the second, like using second derivative, like where like, okay, you find the maximum at the second derivative, like maybe I'm confusing things.
Okay. So I think what you're trying to ask is, when does the second derivative test come in, right?
Yes.
Okay. So for these questions, if you see, it is being pointed out that you're dealing with a minimum point, you're dealing with a maximum point, you're dealing with the largest possible area, you're dealing with, where is that? The largest area. Now, the second derivative test, if I don't know, have you checked out the earlier video I posted in the group?
No.
Okay. So the second derivative test only comes in when you want to determine the nature of the turning point. When you're just finding a turning point, all you have to do is get a derivative. There are 3 steps, actually just 2 steps that I indicated in that video. So when you're trying to determine the turning point, the first thing is get the first derivative and equate it to 0. So here you're just trying to find the turning point, where it is, because you know that is going to be your stationary point. It might be a maximum, it might be a minimum. All you know is that the first derivative must be equals to 0 at a stationary point. So you get the first derivative, equate to 0, and solve for the values, the value or the values of x at the turning point. So it will give you the values of x at that stationary point or those stationary points. Once you have found the values, you then substitute. Here, of course, you're getting the coordinates of the turning point. So you're getting the coordinates of the turning point. In the first step, when differentiating and equating to 0, you got the x values. When you substitute the x values one at a time into the original expression, you're getting the corresponding values of y for each turning point. So the idea is, suppose you have a function like this, where you have a turning point here, a turning point there. By differentiating and equating to 0, you get the value of x at this point and the value of x at this point. And then when you substitute this into the original function, it will give you the corresponding value of y. Let's say this is the y-axis. It will give you the corresponding value of y. And when you substitute this value of x into the equation again, it will give you the corresponding value of x. So here you're just getting what the turning points are. Then the second part would be, what if they now want to determine whether such a turning point is a maximum, a minimum, or a point of inflection. Now that is where the second derivative comes in. So if you look at this in the recording I made earlier on, the nature of the turning point, this is where you have to get the second derivative. So we're not using these steps in our calculations tonight because we're not trying to find the turning point. We're just trying to take advantage of the turning point to determine certain conditions of a particular question. What I mean is, in the questions we are currently solving, they keep specifying that you're dealing with a maximum. You want the area to be maximum. So we come up with an expression for the area, and then all we know is if it's going to be maximum, then the derivative has to be 0. And then we solve and determine what that maximum area has to be. Have I answered your question, Zamila?
Yes, you have. Thank you.
Nice. Okay, so yes, there's another question.
For this question that we're just from solving, if they asked us to find, or if they said the square of the two numbers is a minimum, does that mean we would have gotten the 0 for B and the A for 60 as our numbers?
No. What determined the set we got was this part here. 2 negative numbers. The argument there was that 0 is not a negative number. Because of that, then perhaps we shouldn't use that set. Even if this statement would have been minimum, the approach would have been exactly the same. Because whether minimum or maximum, the first derivative has to be equals to 0. So if, let's say, this condition was not there, then most likely, let's say not the negative number part was not there. If they just say the sum of the two numbers is 0, so two numbers have their sum 60, not 0. If this term was not here, two numbers have the sum 60. That would have implied that both sets would have worked. I hope you're getting that. Both numbers would have worked, but yes, I get what you're saying. The product would have been a 0 because the product would have been the other pair. Because if one of them is actually a 0, what you'd see is that the product, the minimum most for the product would have to be a 0 when one term is a 0. So if this was not there and we are looking for a minimum, if we're looking for a minimum instead, yes, would have gone to the other set because the product is the one that has to be minimum. So if we compared the two, the answers we got, multiplying this and this would give us the maximum possible number, but multiplying this set would give us the smallest possible number. Have I answered that?
Yes, thank you.
Yeah, cheers. Okay. So one thing I feel this question was also trying to just prevent by saying that both numbers are negative is if it was left open that one of the numbers could have been negative, the other one could have been positive, then a minimum could have been subjective. A minimum could have been I don't know how to say this, because if one of them is negative, the other one is positive, notice that it would have been possible to have a minimum when the product was negative this side. When one of them is negative, the other one is positive. So the minimum would have probably ended up being this case. So, okay, let me say it like this. I found the right way to say this. If one of the numbers was positive, the other number negative, most likely the question would have read, find the minimum. Because the minimum of the products would have to occur when one of them is negative, especially the one which is not squared, when it is not negative. So that negative A times the other term ends up giving you a negative solution. Okay, I'm seeing the recording device is struggling. Is it okay now? Okay, so but by saying that both numbers are negative, it's like they're trying to eliminate that the possibility of them first giving you a zero on one, a negative on one side, so that everything that you get is hopefully just positive. I don't know if you guys are getting that. All right, let's move on to the next part. For the next question, it's a similar idea again. They're saying the largest possible area for an isosceles triangle. Find the largest possible area for an isosceles triangle if each of the two equal sides is 10, so has dimension 10. Okay, so isosceles, how does it look like? Well, here's what we're looking at. Let's create our isosceles triangle, something like this. We can work with this. So let's say these are the two equal sides. So we have a 10 here and we have a 10 this side. So, and then they're saying that we want this area to be maximum. Is that the case? Yes, find the largest possible area. So if we're going to have the area there, how do we get the area of a triangle? What's the formula for area of a triangle? Who can give us that? In this case, how would you get the area? How do you get it, guys? Okay, yes. So the area has to be half BH. Now the question is, where is our B? Where is our H? So let me label this this triangle. So we have A, B, C. So what you have to see is that for this formula to be to work in this case, the B has to be from A all the way up to B. This is going to be your base. Apart from this being your base, you also need your height. Your height is going to be a line that runs from C here, from the topmost point, and it has to be perpendicular to your line AB. So in this case, this is going to be your height H. So we're going to now use B down here and H to get what the area is. So our formula for area written down, that is half BH. But we have a number of these things missing. We don't know what H is. We have no idea what B is. So let's start hunting for what that H is. Now, to find what H is, we now look at this shape and just focus on one side. So if we try to just focus on one side, just one of the right angled triangles, you can see that since the whole thing from A to B, this was B, as in small letter b, what this implies is that just from this part, from A, just up to the midpoint here, since that line H is a perpendicular bisector, it means that it cuts AB at the halfway point. So this light blue line has to be the whole length B, but just halved, so divided by 2. With this in mind, we can then create a relationship between the 10 here, the B over 2, and the H. We can create such a relationship. How will the relationship look like? Well, this is now a right angled triangle, so it will be governed by Pythagoras theorem. So by Pythagoras theorem there, we have the longest side, which is 10 squared. This has to be equals to the sum of the squares of the two shorter sides, implying that it will be B squared, or let me say B over 2 squared plus the other side, which is H. So plus H squared. By Pythagoras theorem, we have this. Then this becomes 100 here being equals to B squared over 4. Then plus H. Here we can make H the subject of the formula so that we have 100 minus b squared over 4 being equal to h squared, so that h will be equal to the square root of 100 minus b squared over 4. This becomes the expression for h. We can then get this expression. Let me label this as 2 and this as 1. We can then get that expression and substitute it in our expression for area. Our area from equation 1 was half BH. Now we can plug in what our H is, so that we have half our B, and our H is root 100 minus B squared over 4. This becomes our expression for area. Now, notice that we now have a function that gives us area, and this function is telling us to say that our area actually just depends on what B is. Now, the question tells us one thing. Now we go back to that condition, the working principle. Find the largest possible area for this isosceles triangle, the largest possible area. Now, since that's talking about the largest possible area, it implies that the area here must be maximum. If the area has to be maximum, then its derivative dA, dB, this has to be equals to 0 if the area is to be maximum. Because of that, all we have to do is get the derivative. So again, you're seeing that it's literally the same thing. Get the two conditions that have been given, write expressions using those, and then connect them. So let's get our function. So to get the derivative here with respect to b, we're seeing that this derivative, we can differentiate it by product rule, and then somewhere there we'll have to use chain rule. So let's say, let me just get it down. So this is our expression here. Okay, so you can say let u be equals to 1 over 2b, and v, we can let v be equal to, that's 100 minus b squared over 4. So from here, oh, this is a root, 1 over 2. So that's for the root. So I hope you've seen that I've divided my expression into two parts, half b, and the other part, which is that root there, which is my v. So I'll use product rule here and say the derivative of a with respect to b will be equal to, I'll first differentiate u, I'll keep v the way it is, then plus, now I will keep u the way it is, and I will differentiate v. So let me get what these derivatives are. So let's start with u prime. U prime with respect to b, I am just differentiating what that is. So that is just going to be half. The problem is with v. So v prime, on the other hand, I'll use a chain rule. I'll first differentiate the whole thing. I won't touch what is inside. So the half will come down. And I'll keep what is inside exactly the way it is, minus b squared over 4. Now the power will reduce by 1. So it's going to be half minus 1. Of course, half minus 1 is minus half. Now, in the second part, remember how that chain rule goes. I've differentiated the function. Now I'll differentiate what is inside here. And what is inside, there's 100 there. The derivative of 100 is 0. The derivative of what follows, this is going to be minus. I'm just differentiating that b there. So it's going to be 2b to the power 1 now when I reduce the power for the b, and then over 4. So this is what I am going to have there. So I can then reduce the v prime. The 2 and the 4 can reduce. That's now 1 over 2. So the 1 over 2 and the 1 over 2, I now have 1 over 4. The b here, then 100 minus b squared over 4 to the power minus 1 over 2. So this is what my v prime is. Are we okay with that differentiation there? Any question there? Okay, great. So we can then substitute to get what our dA, dB is. So remember, I'm saying it's V first, then U prime. My V is that square root. So my V is, let me just copy it. That's my V. I just don't want this part. And then I'm multiplying this by U prime, and my U prime is half. Then plus, the next part is U. My U is, where is my U? Half B. That is half B. And then multiplying this with my V prime. And my V prime is all this. So just bring it here. Okay, I'm running out of space there. Okay, so this is the derivative that we actually wanted. So the only thing left here is to simplify this. So I can write this as, this is the same as the square root of 100 minus, that's B squared over 4. And then this is over 2, the half there. The whole square root thing is over 2. Then plus the second part here. Notice that I'm seeing this B here and this B here. I get B to the power 2. Then I'm seeing the 2 and the 4 here. I get 8. So here I am getting B squared over 8. Then there was something which was negative here. This one here. This was negative. Yeah, I remember that was negative there. So this negative here has to make this term here to be negative. Because of that, the 1 over 4 here is negative, so that my expression here is going to be negative. We forgot that negative. I hope you guys were able to see it there. So everything else is still the same, except that negative that we forgot, which makes the sign on the middle to be negative. Then once that is done, I've taken care of that, the only thing left is this part here. That part, you should see that the power there is a negative half. And I hope you are thinking about what that negative means, what it is going to do to this expression. Okay, so at this point, we can now simplify this. We are literally done. We have to equate it to 0 eventually. I'm just trying to dilly-dally here and there, but eventually we equate it to 0 if we're going to end up with the maximum. Okay, so let's see what we have. We have the 100 here minus B squared over 4 over 2. So let me just do this in the background without the recording. Let's continue. Okay, so we've reduced it up to this point. The only thing that is now left here is to take advantage of the fact that the area is supposed to be maximum. So if the area is to be maximum, then dA, dB has to be equals to 0. And since this is our dA, dB, so we're now just going to get this and equate it to 0. So get this, and we'll say has to be equals to 0. At this point, we'll just move the terms around. So we'll take the root 100 minus B squared over 4 over 2. This has to be equals to B squared over 8. I can write it as B squared over 8, or you can see that the 8 can join the square root down here because they're both in the denominator. So B squared over 4. At this point now, we're just solving this for B. You can say, to get rid of the square roots here, you can just square this, square the left side, square the right side as well. This is going to help us take care of those two square roots. We don't even have to square twice and so on. Just square the left, square the right, and the square root goes away. So I'll square the left, and I'll also square the right. If I do that, on the left, the numerator remains only as 100, minus b squared over 4. The denominator remains as just 4 because the square root of 2 is 4. On the right-hand side, I'll square the numerator and I get b to the power 4. And in the denominator, when we square the 8, we get 64. When we square the next part that comes, the square root disappears and we get 100 minus b squared over 4. This is what we end up with. Now we can write this as a single fraction. So we can cross multiply here so that we get the 100 minus b squared over 4 multiplying 64. So I can say multiplying the 64 and then the 100 minus b squared over 4. And then this is equals to 4. And then we have that b to the power 4. So this is where we are. This is now 64. And then we have this 100 minus b squared over 4 squared, because it's multiplying twice. It's this, it's also that. So this is equal to 4b to the power 4. When I look at this term, so look at this term here. It seems like something that is going to be very complex for us to solve. I was even thinking, are we going to end up with a polynomial here? Are we going to start using long division again? We won't. There is actually a shortcut on how we can simplify this. Can you see it? Can you see the shortcut on how you can reduce this without expanding this part? Can you see what you have to do?
I think we can take the square root of both sides.
Nice. You can take the square root of both sides. Notice that all these terms are perfect squares. All these are perfect squares. So take the square root on both sides. So if I was to take the square root this side, notice that the square root of 64 is 8. The square root of this will eliminate the square there, so that I remain with 100 here, minus b squared over 4. The square root of the 4 this side, when I go to this side, the square root of the 4 will be 2. The square root of the b to the power 4 will be b to the power 2. Now this seems like something we can actually work with. 2 can divide into this so that we remain with 4, and then the 100 minus b squared over 4 equals to b squared. And then from here, we can solve this for b. The 4 can be sent inside so that we have 400 here minus, when it comes here, it will cancel with the 4 in the denominator, leaving only b squared. And then this is what will be equals to b squared. Guess what? We won't even have to solve the quadratic equation because this one resolves on its own. We get the 400 here equals to b squared. When the other b squared crosses, we now have plus b squared. This is now 400 is equals to 2b squared, and b squared is now equals to 400 divided by 2, which is just b squared is equals to 200. So that b will be equals to the square root of 200. This is what our b is going to be. What will be the answer here?
$14.14.
Okay, 14.14. So those trying it out, did you find the same answer?
Yes.
Great. So the question was asking us to find the maximum area. So notice that all we needed was actually b. It was actually just one term, either b or h, then getting the area will be easy. So once we have what b is, we can come back to our expression for area, the expression that we were differentiating. Where is it? That was here, somewhere here. So this was the expression for the area. So there's even no need for us to find what h is. Once we have b, we can get what the area is. So we can come back to our expression here. And where there is B, we'll put that value for B. So we'll have what the area is going to be. So this is going to be by 14.14. Then multiplying the square root of 100. Yes, please.
Sorry, a question.
Go ahead.
Leave our answers in third form or in decimal form.
What did I advise you to do in your lectures?
Sorry.
What did I advise in your lectures?
Sorry.
Then you'd have to leave it in this form or simplify it a little bit further. So you can, if you're going to leave it as a SAD, then of course you know to say you can express this as 100 by 2, and the root of 100 is a 10. So this will be 10 root 2. So then you can bring that 10 root 2 here. Is that okay?
Yes.
Okay. So of course it would imply that in this case you are bringing that same 10 root 2 here. And then here you also have that 10 root 2. But when you square it here, the 10 root 2, notice that it will remain only as a 200 because it was root 200. Then root 200 squared, it will just be 200. So half of the 10 there will be 5 root 2. Then multiplying, this is now root the 100 minus. Let's see what is happening here. So we have, oh, that's okay. That's 200 divided by 4. That's literally just 4 into 20, which is 5. So we have a 50 here. So that we have 5 root 2. And then we have the difference there that is going to be a 50. So that is just root 50. So we can try to simplify this. That's a root. So this is the same as root. Can you predict what the answer will be without a calculator? Yes, Kondwani. 50. Will it be 50? Yeah, 50. It will be 50. Nice. It will be 50 in the sense that when you look at this part, this is the same as root 2 by 10, by 50, I mean, which is just root 100. So this is now 5 root 100, and root 100 is 10, which gives us 50 here. So that is our area. So what we're given the units of the side. So I think from the question, they didn't specify what the units for the 10 was. So because they didn't specify the unit for the 10, we still know this is area. We don't want to just leave this as just a number like this. So do you know what you have to say here? How will you give this 50 here? Yes, Kondon. Yes, Kondoni, you can give us the answer. No, centimeters squared would be wrong here. They haven't specified that these are centimeters. And meters squared would also be
Unit squared.
Yes, units squared is better. So you can say unit squared, or you can actually say square unit. So you can say square units, or you can say units squared. All right, like this, or you can write the full word. So that's one thing that you do when the units have not been specified. Don't assume it is centimeters, don't assume it is meters. Just generalize it, whatever the unit is, but squared. Okay, that answers the second question. Any questions before we move on to the next? You see, well, the further we go, the more interesting they get. I looked at these questions before we started, but I didn't really try them out. So yeah, I'm getting first-hand experience together. So we black out together here. It's me and 19 others failing a question, which is not right. Let's look at question 10.
I have a question, sir.
Go ahead.
like if it was asking to find the minimum, just for example, you have to equate it to 0 as well.
Yes. Regardless of whether it is minimum or maximum, at that point, the derivative of the area with respect to whatever the variable is has to be equals to 0. Whether it is minimum or maximum, this doesn't change.
All right, thanks.
Yeah. Okay, so, and to demonstrate that, does this demonstrate that question? No, this, you're talking about largest. The last question, the one I'm saying I'll leave for you guys, we see that it has minimum there, but the approach should still to use the same method. Okay, so let's look at this one. This looks interesting. Look at that ellipse there in the mix. A rectangle with sides parallel to the coordinate axis is inscribed in the ellipse, and this is the form of the ellipse. Find the largest area for this rectangle. Now this looks interesting. Let's see how it goes. They haven't given us a single thing, a single value. Most likely, we will have to leave our answer as just an expression for the area. We might not find the answer. Okay, so what is happening there? Well, here's what they're saying. If you look at the ellipse that they're describing, what we have is x squared over a squared plus y squared over b squared is equals to 1. This is the general formula of an ellipse. But what type of ellipse is this? What can you say about this ellipse?
It's centered at 0,0.
Yes, it's centered at the origin. Whether it is an ellipse like this or an ellipse like this, we have no idea. All we know is that it is centered at the origin. So, well, that second part for whether it has measure in the vertical or measure in the horizontal, that will not actually even matter. All that we'll look at here is it is at the origin. Okay, this looks better. I think it does. Okay, so we have our y-axis here and our x-axis this side. Let's try to visualize our problem. In this case, the question tells us that this ellipse is centered at the origin. So I'm going to put it as an ellipse like this one. Center at the origin. Now, here we're just generalizing things. We don't have a single value. So if we have a rectangle inside, because they're saying this rectangle is inscribed inside our ellipse. Okay, so they're saying our rectangle is inscribed in our ellipse. So to inscribe just means that the rectangle is completely enclosed inside the ellipse and its vertices lie on the line of the ellipse or on the circumference of the ellipse. In other words, we can say that our rectangle is a rectangle like, let me draw, let me not do that. It's like we have this. Then let me copy this line. So it's like we have something like this. Looks better, looks okay. And then we have something like this. Doesn't look good. I don't like how this looks like. Let me start with a vertical line here. I think, is that vertical enough? Don't feel right about it. But anyway, it doesn't matter if we actually get it right in terms of the vertical line, but all that matters is you guys get how we are actually going about this. Okay, so I'll just draw them roughly, even if they're not perfect. You guys get how it works. That's okay. Okay, I think I've destroyed my line. And then we have this face here. It's not perfect. Yeah, it's not perfect, but I hope it will help you guys understand regardless. Since this is inscribed inside our ellipse, what you have to get, something that maybe my diagram is not presenting very well here, is that the line from here to here and the line from here to here, these two lines are the same. And the line from here to here, and also from here to here, these two are also the same. So this is what our rectangle is. It's literally inside. Our rectangle, if it's going to meet these conditions, the rectangle must also be centered at the origin. That thing has to come out clear. Now, if you guys insist, I can try to draw this rectangle perfectly. But I hope you...
No, it's okay.
It's okay, great. Okay, so what it implies is that, let's pick some cases, because if you look at what we're going for, we're looking for the maximum area for our rectangle. The question is saying, find the largest area for this rectangle. So if we're going to have the largest area for our rectangle, let's assign it some dimensions. So to calculate area, we know to say for a rectangle, we use L times B. Let me say length times, let's say width. Let's say something like this. Now, what will be our length? What will be our width? Because I'm saying from here to here, these two dimensions are the same. So let's say this is at negative B. This implies that this one here has to be at positive B. Also, we can say that this one here, from here to the bottom, this one is at negative A. This is negative A. If this is negative A, then from here all the way to the top, it must be positive A. So this tells us what the coordinates of this point is, the coordinate of this point is, and the coordinate of this point, and also the coordinate of this point. These two, or those points, can actually be determined using A and B. Now, with that done, what you should see here is that if we take the length to be the vertical part, the length to be from here to here, can you see what the length will be in terms of B, in terms of A, I mean? What will be our length?
So A?
Yes, the length will have to be 2A. So our area will now be the length 2A. Notice that in the same way, our width, I mean, will have to be from here all the way up to here. And it can also be expressed in terms of B. So the full length of B, that can be taken as 2B. So that in the end, the area can be written as 4A times B. Okay, so I hope that part is okay. Is that fine?
Sir,
Yes.
it's okay and B are confusing me a bit. Is it okay if we use L?
The A and B are confusing you how?
Like, since we already have like how how the vertices of
Oh, okay. I get you. Let's do this. Let's move away from A and B. Yeah, since, yeah, you might say those can be related to the vertices and so on. Instead of A and B, let's say this is in the y-axis. Let me say this is y, negative y, and this is positive y. And I can say from here to here, this is negative x, and this is positive x. How is this?
better, thank you.
Okay. So what this implies is that for the length which is in the vertical axis, we have 2y multiplying the width which is in the x-axis, we have 2x. So that this becomes 4 xy. This becomes an expression for our area. So this is fine. Now, the next part is that limiting factor. And that was the fact that this rectangle must be enclosed inside that ellipse. So what is the expression for the ellipse? Well, the ellipse is this one. This is where our shape has to be enclosed. So our ellipse must be enclosed inside this expression, or not our ellipse, our rectangle has to be enclosed inside this expression. What you have to get is that at the points where these two are actually, let me say at these points, at the vertices of the rectangle, the value of x for the rectangle will be the same as the value of x for the ellipse. So they actually share the x and y variables at these 4 points. Because of that, it's actually possible for me to make one of these variables subject of the formula and plug it in my expression for area. That is the key thing that you have to see. Do you get that?
Yes.
Yeah, that's our driving force. Because what we now want to do is we just want to make one of these the subject. How we make it completely up to us, but we just want to make one of these variables the subject. So if we can make one of these the subject, then we can just come and substitute. So let's say we wanted to make y the subject of the formula. Well, there are many ways you can make y the subject of the formula here. And in this case, let's start first by multiplying with a squared. If I multiply the whole expression by a squared, look at what I get. I'll have a squared here, and the a squared will actually cancel with my a squared down. So I'll remain with only x squared here, plus this side I'll have a squared y squared over b squared. Then this will be equals to a squared. I have eliminated a squared here. Again, it's up to you which method you want to use to make y subject. Next, I can get rid of the denominator from the y squared term by multiplying with b squared. Doing this will now give me b squared here, x squared here, plus the b squared will cancel from that second term, leaving me only with a squared, y squared, and the right-hand side, a squared, b squared. Is that okay? So again, we're just making the subject of the formula. You could have just made this a single fraction and then cross-multiplied. You still would have ended up here. Where? Yes, Richard?
Yes, answer.
Go ahead.
Just the first part, 2 and 2, the network is pathetic.
Okay, which first part?
The first part, that part where you said, where we put in the 2 and the other 2.
While writing the 2, or this
First
2?
part is equal to 2.
This
Yeah.
part?
Yes. 2 and 2 x's.
Oh, okay, okay. So we're saying y is the distance from here to here. This is y. So since we are going down, this part is negative y. And here we're going up, this is positive y. So the length, if I took the length to be this vertical part, then what this implies is that in our case, the length will have to be y up to here plus y also all the way up to that point. So this ends up being 2y. Our length is 2y. Is that okay? Is Richard okay? In the same way, from here to here, this is x, then again x here. So the full length is x plus x, the width. The full width becomes 2x. So I was just focusing on my rectangle. So my rectangle is like this. But from here to here, this is x. This is also x here. So the full length from here to here is 2x. Then also in the vertical axis, from here to here, this is y. And from here also to there, this is y. So the full length in the vertical axis becomes 2y. So to get the area, we multiply the length, which is 2y, times the width, which is 2x. So that is how we reached that part. We multiplied the 2, we reached here. Now we went to the ellipse. Our shape has to be enclosed inside the ellipse. And this is where we had this expression for an ellipse. Now, what I mentioned was that since our rectangle has to be inscribed, it means that the vertices of the rectangle have to lie on the ellipse, implying that at this point, for example, the x value of our rectangle will have to be the same as the x value of the ellipse. This will be true even here. The x value of our rectangle has to be the same as the x value of the ellipse. It's not just the x value. Even the y values will be shared at those points. Even down here, the x and y values of the rectangle will be the same as the x and y values of the ellipse. Same applies to this last point. Because of that, we then realize that the value of x here and the value of y here can actually be associated to the values for our ellipse here, the value of x, the value of x, and the value of y. Okay, so try to what you want us to repeat. Okay, so this part here now, we said we can just make one of these variables subject to the formula. No, it's okay. We did. All right, cheers. So just making one of these subject to the formula so we can make it a single fraction. Let me do it the usual way. Making a single fraction here, common denominator will be the product there, a squared, b squared. Then ax becomes b squared, x squared. That's for x squared, I mean. Then plus y squared becomes a squared, y squared. This is what will be equals to 1. And just like in the method that we used earlier on, when we now cross multiply here, we see that we get b squared, x squared, plus a squared, y squared is equals to a squared, b squared. So you could have used the earlier method that I demonstrated, or you could have gone ahead with this approach. Okay, so from here, of course, we have everything set up. We'll make y the subject of the formula. So what we're going to have is a squared, y squared is equals to a squared, b squared minus b squared, x squared. So this is if we make, we're trying to make y subject. Divide both sides by a squared so that we have y squared is equals to a squared, b squared minus b squared over x squared, multiplying x squared divided by a squared. Then square root from here. This becomes y is equal to the square root of a squared, b squared minus b squared, x squared over a squared. So this becomes the expression for y. Once you have the expression for y, you then go back to the original function for the area. The area was given by this expression. So this is the expression that gives us the area. But now we have what y is. So you can come this side. But now where there is y, we'll just substitute what that function for y is. So get the area. So at this point now, what you have to do, I hope, is clear. Because since this is the area, the question was asking us to find what? The maximum. Yeah, that was the maximum. So if we check the question, we're trying to find the maximum area. So they're saying, find the largest area of this rectangle. So we have come up with the expression for the area, which was perhaps the hard part. Now, to find what this maximum area is going to be, we now just have to differentiate. So remember again, for the area to be max, for the area to be max, it means that the derivative of the area with respect to the variable. When you look at this expression, a is a constant, b is a constant, the only variable here is x. So we're differentiating our area with respect to x. So this derivative has to be equals to 0. Now, how do you do that? Again, we're seeing a case where we have to use product rule. So with that in mind, you have to use product rule here. Should we work it out up to the end, but having used product rule in the previous example, you guys will be able to pull this one off? Should we do it together, or you guys can try it out on your own? What do you guys think?
We can try it on our own.
Okay.
Practice sake.
All right, great. Okay, so nice. I like the confidence. That's good. Yeah, you do need the practice. Product rule, when you have expressions that are like this, yeah, with the root there, can be tricky. So yes, for practice, you guys can try out this and let's see what you're going to find. So remember how it goes. You first have to get the derivative. When you get the derivative, equate it to 0. So whatever you have here when you differentiate, equate it to 0. After equating it to 0, solve that expression for x. Once you find the value of x from the differentiated expression, you will have to bring that value of x, plug it here as well, and solve. You won't be able to solve it. You won't be able to solve, I have to say, because you don't know what a and b, what they are. But you just have to plug those values here so that you get a full-grown expression for the area in terms of what x is. So that is what you will have to do here. Okay, so I think we can end here. You guys can try to finish this. Let me see what you find in the group. So yeah. You guys can have a good night.